Uh, Good evening, my YouTube viewers. Crystal here. I decided that I wanted to do some work on this agricultural data set. And because when I made that video this morning, we found that vacuum classifier with SVM covered every single example on the E. coli data set. And I thought, well, if that's the case, then I want to use bagging classifier with SVM on this agricultural data set because that's a very seriously imbalanced data set as well. And I want to see if I can address this imbalanced data set by using this model. And so I spent all day long working on it. And as a result of that, I'd like to do a code review for you and tell you what I found. So the first thing that we'll do is we'll say that this data set came from the LinearSVC website, and it was one of their hackathon competition questions. And what we'll do is we'll read the problem statement. Though many of us don't appreciate much, but a farmer's job is a real test of endurance and determination. Once the seeds are sown, he works days and nights to make sure that he cultivates a good harvest at the end of season. A good harvest is ensured by several factors such as availability of water, soil fertility, protecting crops from rodents, timely use of pesticides and other useful chemicals, and nature. While a lot of these factors are difficult to control, for the amount and frequency of pesticides is something the farmer can control. Pesticides are also special because while they protect the crop with the right dosage, but if you add more than required, they may spoil the entire harvest. A high level of pesticide can doom the crop dead, unsuitable for consumption, among many outcomes. This data is based on crops harvested by various farmers at the end of harvest season. To simplify the problem, you can assume that all other factors, like variations in farming techniques, have been controlled for. You need to determine the outcome of the harvest season, i.e., whether the crop would be healthy, alive, damaged by pesticides, or damaged by other reasons. So that's your problem statement. And I wrote my program on Google Colab, and as a result of Google Colab having most of the libraries already installed on it, all I had to do was import these libraries. So I imported Pandas, NumPy, Matplotlib, PyPlot, and Seaborn. Now, after I imported the main libraries that I would be using, I loaded the data set. So I loaded the train and the test and the sample data set. So you can see the train data set here. It's 10 columns and 858 rows. And so we can see the last column is the crop damage. So it's going to be either 0, 1, 2, or 3. And most of them are 0. We loaded the test data set. And the test data set is very similar to the train data set, except for the fact that it does not have a crop damage column. And then we loaded the sample sub, which is what LinearSVC wanted to see. The next thing we did was we just asked to see information about the data set, train and test. So, and then we also described the data set, train and test. So we got some statistical information from both of those data sets. Then the next thing we did was we checked for null values, and the only column that we had null values for was number of weeks used. So what I had to do was I had to impute those null values, and so what I did was I replace the number of weeks used with the median value. Then what we wanted to do was we wanted to analyze the data. So I've got a heat map for you. If you like heat maps, then you can see how the independent variables correlate with the dependent variables. And then we did a group by, just so you can get an idea of how many examples you had of 0, 1, and 2. And then what we did was we did a graph on the target variable. And you can see most of the examples were in 0. A few of them were in 1, and even less of them were in 2. So this means that it's got a really big data imbalance, which needs to be corrected. And then so I did a disk plot on estimate insects count, so you can see that. And then I did a disk plot on crop type, and you can see that. I did a disk plot on soil type, and you can see that. I did a disk plot on pesticide use category, and you can see that. I did a disk plot on number of doses week, and you can see that. I did a disk plot on number of weeks used, and you can see that. And then you can see that because we had imputed that value and we had said that we had replaced all of the null characters with the median, so you can see that the median is the highest value because there were quite a few null characters in the data set. I did a disk plot on number of weeks quit, and you can see that. And so you can see that the number of weeks quit was higher. 0 was higher than anything else. I did a disk plot on the season, and there were only 3 seasons that they accounted for. So the next thing I did was I set up my X, Y, and X test. I set up a variable called ID, which that has test ID in it. And the reason why is because I was going to be dropping the ID from the test column, but I was still going to need the ID. So I had to keep that variable somewhere, so I kept it in ID. The Y variable is train.cropDamage, and the X variable is train.drop ID and crop damage. The X test is test.ID. And then what we did was we checked the shape of these columns, and we found that X and X test, it had 8 columns in the data sets. The next thing we wanted to do was we wanted to scale the data. So we scaled the data for X and X test. And then the next thing we did was we got the mean value and the standard deviation. And then what we did was we defined a variable called fitCalls, which is basically just feature plus string I for I in range x.shape. So that's just the number of columns they had. Then we normalize the data, and we have a data frame with normalized data, and every feature is a column. Okay, and so now we do the actual PCA, that's principal component analysis. We set PCA up for n components equals 2, and principal components farm equals PCA farm fit transform. And then we built a data frame with principal component 1 and principal component 2, so you can see the values in the 2 columns of the data frame. And then what we did was we printed explain variation per principal component. So it's telling you what the variation per principal component is. And now what we're doing is we made a plot. And we made a plot of where 0, 1, and 2 fit into the data structure of the memory. So you can see there's a lot of data there, and it seems to me that the 0, 1, and 2s tend to be interlaced with each other, which means it's going to be difficult for the computer to pick out the right values because it's almost like they're laid one on top of the other. And then what I did was I decided to make a 3D chart. So we've got the code for the 3D chart. And again, we've got this 3D chart here, and you can see 3D how it's just like one big blob of healthy, damaged pesticides and damaged other. But it's one big blob of healthy, and inside of the healthy, you're going to have damaged pesticides and damaged other. So it's going to be very difficult for the computer to pick all this out. And then so what we do is we reverse the PCA. So X equals PCA inverse transform X. And then after that, what we do is we split our X data set into X train, X val, Y train, Y val using train test split. And we had a random state of 1, test size equals 10%, stratify equals yes, shuffle equals true, and then we check the columns of that. Then what we do is we set our class weights. So define this variable class weights, and that's a formula to get your class weights. And we didn't create a pipeline. I started out creating a pipeline, but then because I wanted to put the PCA in there, and since I had the PCA in there, I couldn't have a pipeline. So I had to delete the pipeline. So even though it says create pipeline, we didn't create a pipeline. I took the pipeline out. I put in there model equals bagging classifier, base estimator equals LinearSVC, class weight equals class weights, dual equals false, max iter equals 1000, random state equals 1, fit X train, Y train, and I calculated it. If you wanted to know what the actual class weights were, the actual class weights are up here, but I didn't use them. I just used the formula that I had already defined. And so I printed the model, and it had a 80.33% accuracy. And then what we did was we set our params, so that gives you a lot of information as well. And one thing that's interesting here is it told you the class weight. So they had 0 was 12.80, 1 was 0.39897825, 8049710015, and 2 was 2.40667378596365. So what it did was it determined the class weights itself, and that's what it determined the class weights would be. So now what we're going to do is we're going to predict on the validation set. And when we predicted on the validation set, let's see if I can find it. Oh dear, I can't find it. Surely it was in there. So it made a data frame. So we predicted on the validation set, and it made a data frame. And then what we did was we did a chart on the validation set. So you could see that that's strange. What it did was 0, not very many, 1, a lot, and 2, not very many. And that's not what it was supposed to be. It was supposed to be 0, a lot, 1, not very many, and 2, a lot, not very many. So that's a bit unusual. And then, but what we did was we printed that, we put it on a counter, and then when we put it on the counter, it said 1 was 8,002, 2 was 517, and 0 was 367. So the 1, 2, and 3, or 0, 1, and 2 seem to correspond with the Y val. But what we can do is we can go over here and we can look for the Y val. I don't see that we've got the Y val. But so we don't have the Y val, but we did compare, put it on a counter. So it seems like the values were similar. And then what we did was we put the Y val and the Y pred on a matrix. And so you can see the matrix. So what we had for 0 was 231 for the Y val and 367 for the pred. And what we had for 2 was 1231 for Y val and 517 for pred. And what we had for 1 was 7424 for Y val and 8002 for pred. So the calculations were okay, but anyway. And then so we did actually set it on a confusion matrix, and this confusion matrix gave you lots of information. And then we had some more scores, and our accuracy score was 80.7337%. So there's our accuracy. And then we had some other scores that you could see as well. So then we printed off, after we predicted on the validation set, we wanted to predict on the test set. So predictions came out in an array, and then we put this on a data frame with ID, which is what had been previously made at the beginning of the program, and crop damage, which was predictions. And then so we put it on a data frame, and then we submitted it to Analytics VidHaya. And when I submitted it to Analytics VidHaya, it says I'm not connected. I got like an 80% because I'm looking. It just says right here that I'm not connected. So anyway, it says I'm not connected. So I lost my internet connection. So that's not good. And so basically what I've done is I have completed an entire video with no internet. So that's going to be fun. So I'm going to have to see how much of this video I actually got recorded. But whenever I did put the submission on Analytics VidHaya, I got around an 80%. And then when I got around the 80%, it wasn't as high as some of my other briefings, but I did actually get to address the class imbalance, which didn't get addressed in previous readings. So let me just see if I can find this. So I'm still recording, so let's see how it goes if I'm still recording, and hopefully this video will work out. I hope it does. So if you like my video, please like, subscribe, and share. If you like the work I do and you would like to leave a donation, then I've got my email address for my donations PayPal account in the description box below. I don't have enough subscribers, so I can't monetize, and that's why I have to ask for donations. So thank you so much for watching this video, and I look forward to making more videos for you.